Hello everyone, welcome to Math 115 College Algebra. So in this section I want to talk about power functions and polynomial functions. And in particular I want to talk about how to find the end behavior of power functions and polynomial functions. The end behavior means as the input, as x gets really small, like goes to negative infinity, what happens to the output? And as x gets really large, goes to positive infinity, what happens to the output? Okay, so first let's talk about, before we get into polynomials, let's talk about power functions. So a power function has this form, I'll write it down again here, where we have f of x, right, so it's a function, is equal to some constant times x to some power p. So that's what makes the power function, right? It's x raised to some power. And k and p, so the coefficient in front and the exponent, right, the power, are both just real numbers. So some examples of power functions are the following listed here, right? A constant function could be a power function. Why? Because it has that form, right? 3 times x to the 0. So p in this case is 0, but remember anything to the 0 power, x to the 0 is 1. So f of x equals 3, a constant function, that would be a power function. Or f of x equals x to the 1, right? Remember that's the identity function. That's also a power function, where the k is a 1 here. Or x squared, right? A quadratic function, where the coefficient, the k is a 1, the power is a 2. But also things like the reciprocal function, 1 over x. So now p is negative 1, right? Or the reciprocal squared, f of x equals 1 over x squared, where p is negative 2 and k is 1. Or the square root function, where p is 1/2, because remember, k and p can be any real numbers. Okay, so these are all examples of power functions. Now, we're going to focus on power functions where the exponent, the p, are just positive integers. Okay? So we're going to focus on the power functions where the p here, the exponent, are just positive integers. All right, so here's an example. I'm going to show you several plots. I did this in Desmos. If you want to, you can go on to Desmos and demonstrate that you get exactly these curves. So in this case, right, I have these power functions. First of all the k's are 1. Right, so the coefficient in front is a 1, and the exponents, right, the p's, are all going to be even. We'll start with even values, so 2, 4, 6, 8. So notice, first of all, that all these functions are symmetrical about the y-axis, right? If you flip it, then you get exactly the same shape. And if you look at these plots, the x squared is going to be this red curve right here. So that's the graph of f of x equals x squared. Notice all the graphs actually go through 0, right? When the input is 0, the output is 0 for all of these. And they also all go through 1, 1, and then negative 1, 1, right? Because if I plug in 1 squared is going to give me 1. If I plug in 1 here, 1 to the 4th still gives me positive 1. So they all go through 1, 1. And if I plug in negative 1, because these are even exponents here, I'm going to get positive 1 out as well. So they go through the point negative 1, 1 as well. And as the exponent increases, so the red again is x squared. The blue is x to the 4th. The green is x to the 6th. And the purple is x to the 8th. Notice that as the exponents increase, they grow faster and faster and faster. Right? They get larger and larger and larger. Really, that's when x is greater than 1 or x is less than negative 1. They grow faster and faster. If you look between negative 1 and 1, because now you're raising fractions, right, to a higher exponent, they're going to get flatter. They're actually going to get smaller. So if you look like the purple one, x to the 8th, is really flat here. And then it grows really fast. Okay? But the key thing is, what happens with the end, what we call the end behavior? So as x gets really, really, really large, so the end behavior, as x gets really, really large, like goes to positive infinity, what happens with the function? Or as x gets really, really small, goes to negative infinity, what happens to the function? Well, if you look at these, right, in this case, as x goes to, I usually write like that. So the arrow means goes to negative infinity. So as x gets really, 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 really small, this way, what happens to the function? It grows to positive infinity, right? It gets really, really, really large. If you have these even exponents here, right? If the p's are even integer values, even positive integer values. So as x goes to negative infinity, the function itself, f of x, goes to positive infinity. I'll write the plus just to emphasize it's positive infinity. And then what happens the other way? As x goes to positive infinity, so as the input gets larger and larger and larger, right, in the positive side, what happens? Again, the function goes to positive infinity. So f of x goes to positive infinity as well. Okay, so again, that's what's called the end behavior of the function. So when you have these even positive integer exponents, that's going to be the case. As x goes to negative infinity, the function goes to infinity. As x goes to positive infinity, the function goes to infinity. All right, what if the, and I have that summarized here as well, right? What if the exponents are odd positive integers? Okay, so let's look at those. So now we have x to the 1, right? X cubed, so the cubic function, x to the 5th, x to the 7th, x to the 9th, x to the 11th, and so on. So all the exponents now are odd. The k's are just 1 again, so all these k's are just 1. And if you look at these shapes, okay, so f of x equals x is obviously the line here, right, the red one. Then if I go x cubed, I'm going to get the blue here. They all kind of have the same shape, right? If I go x to the 5th, I get the green, and then x to the 7th, I get the purple graph here. So notice again that as the exponent increases, when I'm past 1 or negative, if I'm greater than 1 or less than negative 1, the function just grows faster, right? This is x to the 1, this is x cubed, this is x to the 5th, this is x to the 7th. It grows faster and faster. In this case, to positive infinity. In this case, it gets smaller and smaller faster, right, as that exponent increases. And then if I'm in between negative 1 and 1, because again, if I take a fraction like a half, right, and I raise it to a higher and higher power, it's going to be a smaller and smaller number. So basically, they get flatter and flatter, right? As the exponent increases, it gets flatter. If you look at x to the 7th, the purple, it's really flat here in between negative 1 and 1. If you did like x to, the say 1011 or something, it would almost look perfectly like flat here. It'd be hard to even tell if you got a really high odd exponent. Okay, so what's happening with the end behavior? Sometimes people call it the long range behavior or end behavior. So in this case, as x goes to, I'll do negative infinity first. So as x gets really, really, really small, what's happening with the function? It's going also to negative infinity, right? And if you have a larger exponent, it goes faster and faster and faster to negative infinity. So f of x goes to negative infinity. And then as x gets really, really large, so as the input gets really, really large, so as x goes to positive infinity, what's happening with the function? Well, as x gets really, really large, it's also going to positive infinity. Okay, so that would be the long range or the end behavior of these functions, these power functions, where the exponent is an odd positive integer. All right, so let's do, actually, let me talk about the k, Because in every case that we did so far, the k was just positive 1. What happens if the k is a negative value? Okay, the first part here, this just summarized if the exponent was odd, right? All right, let me make a little chart here. So I'm going to have a chart where I have P, so if the exponent is even, and then if P is odd, and then I'll have the two possibilities for K as well. So K, remember that coefficient out front, let's say it's greater than 0, right? So it's positive. And then let me do the other possibility if K is negative, less than 0. All right, so if K is positive and P is even, we already know that the shape of the graph is going to look like this, right? And the larger and larger P is, the flatter and flatter it'll be between -1 and 1, and the faster it'll rise. But it'll have that general shape. It kind of looks like a parabola. Okay, so basically as x goes to negative infinity, the function goes to infinity. And as x goes to positive infinity, the function also goes to infinity. Right, so that's what we talked about earlier. And then let me do the odd one too. We already talked about this one. So generally, the shape of the function is like this, right? So if it's x or x cubed or x to the 5th, and in this case, as x goes to negative infinity, the function also goes to negative infinity, and as x goes to positive infinity, the function goes to positive infinity. Okay, now what if the coefficient out front were negative, right? Like let's say I had, if this is say the function f of x equals x squared, what if it were negative x squared? What does that do to the function? Well, actually, it flips it about the x-axis. So in this case, it would look something like this. So in this case, it's the opposite, right? So now as x goes to negative infinity, the function also goes to negative infinity. And as x goes to positive infinity, the function also goes to negative infinity. Right? In both cases, it goes to negative infinity. So it switches the direction. It switches like the long-range behavior or the end behavior. Okay, and then same thing here. So if this were, say, x cubed, what does negative x cubed look like? Well, it's going to flip that graph about the x-axis. So it'll look something like this. Let me see if I can draw that a little better. Something like that. Okay, so in this case, as x goes to negative infinity, now the function goes to positive infinity. And as x goes to positive infinity, the function goes to negative infinity. Okay, so that's going to be true. If the k is negative, it just flips what you would think, right? The graph flips. So the long range or the end behavior is going to be the opposite of what it was. All right, so here, let's do some examples on that. So describe the end behavior of this function, 5x to the fourth. Okay, so in this case, the k is positive, and the p is even, right? So k is equal to 5, right? So that's greater than 0. And then p is equal to 4, which is even. So we know what this is going to look like, right? It's going to have a general shape like this. It'll be a little flatter than this, it'll be a little flatter than the quadratic function, right? Because it's to the fourth power. And actually, the 5 here, what the 5 basically does is it stretches it vertically. So it'll grow a little faster, okay? But it doesn't matter. We just need the general shape. So it has that general shape. So now I can figure out the end behavior, right? As x goes to negative infinity, the function goes to positive infinity. And as x goes to positive infinity, the function also goes to positive infinity. Okay? All right, what about this one? Describe the end behavior of negative 2x cubed. Okay, so now k is equal to negative 2, right? So it's less than 0, it's negative. And then p is odd, right? P is 3, which is odd. So this is going to look like a regular cubic function, but flipped, right? So remember, a regular cubic function will do something like this. But because of the negative 2, it's going to be flipped. So it's going to look something like this. And the 2, by the way, will just make it grow faster. So something like that. Okay, so, and now we can answer the question, right? As x goes to negative infinity, the function goes to positive infinity. As x goes to positive infinity, the function goes to negative infinity. Right? That's the end behavior, or the long-range behavior. Okay. Let's now discuss polynomial functions, which basically, if you look at the definition here, they basically just sums of power functions, right? But the exponent here has to be a non-negative integer, and that's why we focused on the power functions, just where n was a non-negative integer. Because there are power functions in general, the n could be anything. It could be a fraction, it could be any real number. But if n is a non-negative integer, and you add a bunch of those power functions together, you get what's called a polynomial function. So it has this general form here, right? an is the first coefficient. It's called the leading coefficient of x to the n, plus an minus 1, the second coefficient, times x to the n minus 1, plus dot dot dot, all the way down to the constant term, right? And why is that a constant? Well, you really have an x term there, but it'd be x to the 0, right? It'd be a sub 0 times x to the 0. And remember, x to the 0 is 1. So it's just a constant term. Now, the degree of a polynomial is the highest power of the variable that occurs in the polynomial. So it would be whatever the n is, like the highest degree would be the degree of the polynomial. This a sub n x to the n is called the leading term, and the a sub n is the leading coefficient of the polynomial. Okay? So first of all, before we start doing questions on this, let me give you some examples of things that are polynomials and aren't polynomials. So I'll make a little list, a table here again. So if I have something like this, if I have, say, x squared minus 2x plus 5, is that a polynomial? Yeah, that fits the form up above, right? In this case, I have like 1x squared minus 2x to the 1 plus a constant, right? That's a polynomial. In fact, what is this? What type of function is that? That's a quadratic function, right? Which happens to be a polynomial. What if I had this? What if I had f of x equals negative 4x to the 7th minus 6x cubed plus x minus 1. Yeah, that's fine, right? A lot of the terms, so where's the x to the 6th term, x to the 5th, x to the 4th? In those cases, all the coefficients in front were zeros, right? There's no squared term, so that coefficient was also a 0. But this fits the form, right, of the polynomial. So that's certainly, it's like a 7th degree polynomial, because that was the highest power here. Certainly this would be, right, that fits the form. That would be a linear function. And then even if you just had a constant, that would also be a polynomial, right? Because that would fit this form right here where basically all these coefficients are 0, but we just have this constant term, right? This a naught is a 3 in this case. All right, so those are examples of polynomials. What isn't a polynomial? You can think of many examples. Things like, if I have a square root function of something, doesn't matter let's say, that would definitely not be a polynomial, right? It doesn't have that form. Some like trig function, right? We'll talk about trig in the last few sections of this course. That's definitely not a polynomial. If I have a rational function, which is basically a polynomial divided by a polynomial, but it's not a polynomial by itself, so that would not be a polynomial, etc., etc. Okay, so in this case, we're just going to focus on polynomials. All right, so let's look at this example. Identify the degree, the leading term, and the leading coefficient of this polynomial. So the first thing I would do is I would write the polynomial in descending order, which means you write the highest power first. So basically you're going to write the leading term first and then decrease from there. So I have a 6th power, then there's a squared, then there's a linear term, and then the constant. Okay, you don't have to do this, but sometimes it's nice to just write it in descending order. Descending order. Okay, now we can easily pick out these terms and answer these questions. So first of all, what is the degree of this polynomial? Well, the degree is going to be the highest degree, right? So it's like the highest exponent. So basically, this is a 6th degree polynomial. So 6th degree polynomial. All right, what is the leading term? Well, the leading term is the term of highest degree. So that would be the leading term, right? So the leading term would be the negative x to the 6th. And remember, that really means negative 1, right? X to the 6th. And then the leading coefficient is the coefficient of the leading term. So the leading coefficient is the negative 1 here, right? So leading coefficient is the negative 1. Okay, so that's all they mean by, classifying like the polynomial. The degree of the polynomial, the leading term, and the leading coefficient. Okay, so we talked about the end behavior, right, or the long-range behavior of power functions. What about the end behavior or long-range behavior of polynomials? Well, it turns out that when we're talking about just the end behavior, the only thing that matters, the only thing that's going to have any impact is going to be the leading term. Okay, so, and I have that written here. So to determine the end behavior, right, or long-range behavior of a polynomial, we only have to investigate the end behavior of the leading term. All right, so that means we have to be able to figure out what the leading term is. So let's say this is a polynomial that's given. Determine the leading term, degree, and the end behavior. So we could just expand this out, right? Here, I'll do some of these. I'll expand them all the way out. But we're going to find there's easier ways if we just interested in the leading term. But for now, let's just do the whole thing out. So let me expand that second term, or the product of the two factors there. Let me do that first. So I'm going to have to multiply those, right? Basically FOIL them out. So if we do this, we're going to get x squared plus x, right, 1x, minus 2x, and then minus 2. So this is going to be x squared, and then plus x minus 2x is minus x, and then minus 2. And then I need to multiply that by negative 5x cubed. So now I'm going to distribute in the negative 5x cubed. So I'm going to end up with f of x equals negative 5. X cubed times x squared. Remember, you add the exponents to be x to the 5th. Then negative 5x cubed times negative x would be positive 5x to the 4th. And then negative 5x cubed times negative 2 is positive 10x cubed. Okay, so negative 5x to the 5th plus 5x to the 4th plus 10x cubed. All right. What's the leading term? Well, the leading term is the term of highest degree, right? So it's that term right there. So the leading term is negative 5x to the 5th. What's the leading coefficient? Well, the leading coefficient is the negative 5. What's the degree of the polynomial? The degree of the polynomial is the exponent of the leading term, right? It's the degree of the leading term, basically. So this is going to be a 5th degree polynomial. Okay, and then how do we figure out the end behavior, or the long range behavior? We only have to look at the leading term. So it's kind of like saying the polynomial here, which is f of x, is kind of like, I'll do approximate. It kind of looks like negative 5x to the 5th, right? We have these other terms, but when x gets really, really small or really, really large, the only term that's going to matter is this leading term. The other ones will be smaller and smaller and smaller. This is going to dominate, and this determines what the end behavior is, what the shape of the graph is going to look like at the ends. Okay, so, well, what does this look like? K is negative, right? K is negative 5. The P is an odd function, so it's going to have a shape like this, right? Normally, if K is odd, it has a shape like this. If P is odd and K is positive, it has a shape like this. But K is negative, so it flips it, so it's going to have a shape like this. So that will allow us to figure out the end behavior, right? As x goes to negative infinity, the entire polynomial goes to positive infinity. And as x goes to positive infinity, then the entire polynomial goes to negative infinity. Because it only depends on what's happening with the leading term. Okay, it's going to be like the polynomial itself would be very complicated, it may oscillate in between here, but when you get really, really small or really, really large, it's going to look like that. It's going to go up, and then when x gets really large, it's going to go to negative infinity. Okay, it'll be more complicated in the middle here, but at the ends, it'll have this shape. All right, let's do another one here. Okay, so same sort of question, right? Given this polynomial, determine the leading term, the degree of the polynomial, and the end behavior of the polynomial. All right, let's see if we can do this a little quicker though. So remember, I expanded out this whole thing on the last question. But what is, if you multiply, right, this binomial times this binomial and you expand this out, you FOIL it basically, what's the largest term here? Can you guys see it's going to be x squared, right? Because everything else, then I'm going to get a 4x, a minus x, and a minus 4. They're all less than x squared. The largest term I'm going to get here is x squared. So this is kind of like, because remember, we only care about like what's happening with the leading term. This is kind of going to be like negative 3x squared times, and then this whole thing, the largest term is going to be x squared. So this is going to be like negative 3x to the fourth. That's going to be my leading term. That has to be my leading term. So my original polynomial kind of looks like negative 3x to the fourth. All right, so given that, we can answer these questions, right? What's the degree of the polynomial? The degree is a fourth degree, right? It's just the exponent of that leading term. What's the leading term? It's negative 3x to the fourth. What's the leading coefficient? It's the negative 3, right? And then what's the end behavior? Well, what does this graph look like? Well, normally, right, since p is even, if k were positive, it would look like this, right? It would look like a quadratic function, except flatter, because it's to the fourth power. But since k is negative, it just flips it. So it's going to look like this. Again, the actual graph will be more complicated here in the middle, but at the ends, it's going to look like this, right? It'll look like this negative 3x to the fourth function here. So given that, we can answer our question, right? As x goes to negative infinity, the original polynomial is also going to go to negative infinity. And as x goes to positive infinity, then the original polynomial also goes to negative infinity. Right? They both go to negative infinity. As x gets really, really small, it goes to negative infinity. X gets really, really large, it goes to negative infinity. Okay. So in addition to end behavior, right, we might be more interested in like what's going on towards the middle of the function, like near the origin here, but just where it's finite, it's not blowing up to negative infinity or positive infinity. So there's several things that could be happening in the middle. So let me draw a picture here. Let's say this is my polynomial. So it looks something like this. Okay, so there's a few points of interest here. One of them is the y-intercept, and that's something we can easily find. There may be x-intercepts, which we can find. In this case, in this picture here, there's 3 of them. And then there may be like local maximums and local minimums, which are here. These are like turning points, right? This one is a local maximum, and this one's a local minimum. So it's like turning points. There, and then this is also a turning point down here. Okay, so let me write that better. Okay, well, we know how to find the y-intercepts and x-intercepts, right? I'll explain it in easier. So that's doable. The turning points, right, where there's like a local maximum, like a hill, a local minimum, that's harder in general to find without using calculus. So, but we could graph them, right? We could use Desmos and graph it, and then you could at least approximate where those turning points are, okay? So let me summarize like how to find these things. So how to find I'll start with the x-intercepts. Right, which are sometimes also called the zeros, although it's really, or sometimes roots as well. It's really only the x value of the x-intercept that's the zero or the root. Right? Remember, x-intercept itself is an ordered pair, right? It's going to be something comma 0, right? The y coordinate is always 0. But we often just sometimes call them zeros or roots. Anyways, so how do we do that? Well, we know how to do that, right? We set f of x equal to 0, right? Or that's like saying y is equal to 0, and we solve for x. Right, we've done examples of that before, at least with quadratic functions and linear functions. Okay, so that's how to find x-intercept. What about y-intercept? Well, y-intercept, there will always be one y-intercept. We set x equal to 0 and solve for y. I'll say find y equals f of 0, right? So you force the x to be 0, evaluate the function. That means you're solving for y, right? You're setting x equals 0, solving for y. And then the turning points again are hard to find in general. Without calculus. But if you can use some type of graphing software, you can graph them, or your calculator, right? Graphing calculator, and at least approximate where they are, right? You can get some sense of where those turning points, where those relative maximums or local maximums and local minimums are. Okay, but in general, it's hard to find the exact locations unless you know some calculus. All right. So given that, let's do an example here. So I'm given this polynomial, and I want to determine the x and y intercepts. Okay, so here's my polynomial. How do I find? Let's do the y-intercept first. So to find the y-intercept, right? I set x equal to 0 and solve for y. Which again is going to be f of 0 in this case, right? So actually in this case, this is easy, right? Because if I evaluate f of 0, right, that's what we're calling y, it's just going to be 2 times 0 cubed minus 6 times 0 squared minus 20 times 0. That's just 0, right? So basically, the origin 0, 0 is going to be my y-intercept. All right, so that's the y-intercept. And then what about the x-intercepts? Well, now I set the entire function equal to 0 and solve for x. All right, I set y equal to 0, but y is the function now, equal to 0, and solve for x. So to do that, right, I'm going to set this equal to 0, and I'm going to try and factor. It looks like I can pull out a greatest common factor right off the bat, like a 2x, and I'm left with x squared minus 3x minus 10, I guess, is equal to 0, and hopefully that's factorable. Let's try it. This is like the simple case, right? Like the BC rule. I just need to find two things, and multiplied will give me negative 10 and added give me negative 3. And I guess negative 5 and positive 2 will work. Yeah, okay. Great. So now I can set each of those equal to 0, right? So one possibility is that this is true. Another possibility is x minus 5 is 0. Another possibility is x plus 2 is 0. This one just gives me, if I divide by 2, just gives me x is equal to 0. So that's one solution, which again is saying that the origin is also an x-intercept. Then this possibility gives me, if I add 5, x equals 5. So that says that the point 5, 0 is an x-intercept. And then this one gives me the solution x equals negative 2. So that's saying that negative 2, 0 is another x-intercept, right? So these are my 3 x-intercepts. Okay. What if we wanted? It didn't ask, but let's do it anyways. What if we wanted to know the end behavior, right? The long run behavior of this function. Well, that would only depend on the leading term, which is 2x cubed, right? So this polynomial, just in regards to end behavior, it looks like just the leading term, 2x cubed. And we know what that looks like, right? That's something like this. Since it's an odd exponent, right? P is odd and the k is positive, it's going to look something like this. Right? Like a regular cubic function. So therefore, as x goes to negative infinity, the function goes to negative infinity. And as x goes to positive infinity, the function, which is the polynomial in general, right, goes to positive infinity. Right? As x gets really, really small, it goes to negative infinity. As x gets really, really large, it goes to positive infinity. Now, does the actual polynomial look like this? No, this is only the leading term, right? But because it's going to do something more complicated in between. In fact, we know that it has to have these x-intercepts and that y-intercept. Again, you could graph it, but when you get out really far, it's going to look like this. It's going to go down to negative infinity. When you get really positive, it's going to go up to positive infinity. Okay, and then one last thing about the graphs of polynomials in general. I'll review here. So a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So knowing that we can usually come up with what is like the least possible degree of a particular graph that represents a polynomial just by looking at the x-intercepts and the number of turning points. Okay? So, and it turns out that actually looking at the number of turning points is going to be more important. So here, I'll give you some examples here. Let's say I have a polynomial that looks like this. I'll draw a few of them. Then I have one that looks like this. And then I'll do a line as a polynomial, right? Say a line looks like this. So in this first case, I have two x-intercepts and one turning point. Right? Two x-intercepts here and here, and then it just turns once. One's turning point. Here I have one x-intercept and two turning points. It turns here and turns here. So one x-intercept and then two turning points. And then with the line, I basically have one x-intercept and zero turning points, right? Because it doesn't turn at all. So I have one x-intercept and zero turning points. All right, so the question is, how do I come up with the least possible degree? Like, how do I figure out the degree of these polynomials? Well, it turns out the x-intercepts doesn't really help us that much, and I'll explain why. Because you could have one, but this if this polynomial were shifted down a little bit, right, it could actually have three, right? So it doesn't really help us. It's going to be the turning points. So again, if you look at this, it says, this definition says a polynomial of degree n will have at most n x-intercepts, and this is the important thing, n minus 1 turning points. So if you want to figure out what the degree of the polynomial is, if you add 1 to the number of turning points, that's going to be a really good estimate, right? So in essence, you're figuring out the least possible degree, right? Because the shape, it might be really hard to determine exactly like that this would be like a degree 2, okay? Or this is the degree 3. But that's how we're going to answer this question. So we're going to look at the turning points, right? So because this first one has one turning point, and we know a polynomial of degree n has n minus 1 turning points, then the degree of the polynomial must equal the number of turning points plus 1. Right, so in this case, the degree would equal 2. Okay, what about the second one? Well, it has 2 turning points, right? So the degree is going to be 2 turning points plus 1. Degree will be a third degree polynomial. All right, which makes sense, right? This looks like a quadratic function, right? That's a second degree polynomial. This looks like some type of cubic function, third degree polynomial. And then for the line, the degree, actually we know because it's a line, right? It better be 1 degree. Does it follow this? Yeah, it has 0 turning points plus 1 will give me the degree, right? So the degree is equal to 1. It's a linear equation, right? That gives you a line, okay? So again, the reason why you can't go by the number of x-intercepts is this, like this middle function here, it could have done, what if it was shifted down a little bit? And it did this. So it's basically like the same function, just shifted down. But now if you look at it, it has 3 x-intercepts, whereas before it only had 1, right? So that doesn't really help us in determining the degree of that polynomial. But it still has 2 turning points. So if I add 1 to that, 2 plus 1, it's still a degree 3, right? That's a third degree polynomial. fact, it's the same equation, just with you're going to have a smaller constant term. You have to subtract to shift it down by that amount. So that's why you really can't go by the x-intercepts. You have to go by the turning points. So the degree is going to be the number of turning points plus 1, right? And technically, it's like the least degree because we don't really know the shape of this, but assuming this is nice and smooth, this would definitely be a third-degree polynomial. Okay, in the next section, we're going to talk a little bit more about graphs of polynomial functions. And by looking at graphs, actually, we, in many cases, will be able to come up with the actual equation itself, the expression for the polynomial. All right, great, thanks.